Now that we have some practice finding the sampling distribution of sample means, I want to take a closer look at the distribution itself. So if we're looking at the sampling distribution of sample means or averages, and as long as we meet certain conditions, those averages are guaranteed to be distributed normally, and we'll use the mean from our sample, and then we'll take our population standard deviation sigma and divide that by the square root of n, or our sample size. So one of those conditions that allows us to use that formula for the sampling distribution is that if the original population is distributed normally with the mean of mu and a standard deviation of sigma, then any sample size will turn out that that sampling distribution is also normally distributed and follows that formula. So the first question I want to take a look at is, why can we use the sample mean x bar to represent the population mean mu? So I want to revisit that sleep time problem from earlier. So recall that first sample of 100 had a mean time of 509 minutes of sleep. The second random sample of 100 had a mean sleep time of 530 minutes. They kept repeating that over and over again. And what they found is that the sample mean x bar follows a normal distribution with the same mean as the original population distribution, so 528.8 minutes. So what that's illustrating for us is that if we keep taking larger and larger samples, that sample statistic, the mean, x bar, is guaranteed to get closer and closer to the population mean, mu, so that essentially we can replace them with each other, or we can say that x bar is equal to mu. So this really incredible fact is called the law of large numbers. And what's really fascinating about it is that it holds true for any distribution, whether it's normal, whether it's skewed, whether it's uniform, no matter what, this is always going to hold true. So our formal definition for the law of large numbers is that if you draw random observations from any population with a finite mean mu, as the number of observations drawn or as your sample size increases, our sample mean x bar is going to get closer and closer to the population mean mu. So over on the right, you'll see a picture of a graph, and this is going to illustrate this law of large numbers for us. So if I have a fair coin and I'm flipping it, the percentage or proportion of heads I should get is 50%, assuming it's fair. So that very first time I flip that, my proportion is either going to be 0% or 100%, which is very far away from 50-50. If I flip this coin 3 times, maybe I'll get 1 head, which is 33%, or 2 heads, which is 67%. So that's getting closer to the 50-50 split. And as I keep flipping this coin, maybe I flip it 100 times and I get 48 heads and 52 tails. So closer to that 50-50 split. As I keep going, I flip this coin hundreds of times, thousands of times, tens of thousands of times. What's going to happen is that that value of heads is going to settle down to 50-50. So in other words, the sample mean x bar is going to get closer and closer to the true population parameter, the true population mean of 50%. And so the law of large numbers, what that allows us to do is with that sampling distribution, we can replace the mean mu with the mean from our sample.